Okay, I will continue exactly where we finished last week. Got to hit the ground running and move quickly because I'm a bit behind schedule. So we have this thing which I call the category of lenses, where the objects of this category are pairs of sets, which I will write like x plus, x minus, and the morphisms are these things which I will call lenses, which are pairs of functions so specifically, this is for a morphism x plus x minus to y plus y minus, which I'll call lambda, is a lambda plus, which is a function from the set x plus to the set y plus, and a lambda minus, which is a function from x plus times y minus to x minus. So I claim that this forms a category, which I think I covered enough last week what that means. So we need to give the structure of a category. So on any object, which is some pair of sets, we need an identity morphism. So that has to be some lens from x plus x minus to x plus x minus. So along the top, we need a function from x plus to x plus. That's going to be the identity function. And along the bottom, we need a function from x plus times x minus to x minus. That's going to be the right projection. And then composition is going to take a bit of work. So if we have some lens like this and some other lens like this, so we need a composite. So we need a lens from x plus x minus to z plus z minus. Along the top is easy because we can just compose the functions from x plus to y plus to z plus. And along the bottom, I'm now going to write this down. So lambda mu, the composite, minus, so this needs to be a function from x plus y minus, x plus times z minus to x minus. So we're given as input some point of x plus, I guess I'll just write this x, which is in x plus, and some z, which is in z minus. And I can just write down the formula for this. This is going to be lambda minus of x together with mu minus of lambda plus of x and z. Okay. It's not, I think, obvious just from staring at it that this actually forms a category, which is to say that this operation is associative and that the unit I defined is actually the unit of this composition, but it turns out that it is. So I've written this for sets and functions. If you know category theory, the minimal setting in which you can do a construction like this is starting from any category with finite products. So in particular, in this category of stochastic functions, this does not have finite products. So we can't do this trick over the category of stochastic functions. So we can't talk about stochastic lenses directly. Later I'm going to come back and say how we can do that with an amended definition. Okay. I mean, I could go through the proof that this is associative and so forth, but it's just, at this point, there's no. I mean, you could do it in a pretty way, but the easiest way to do it is the unpleasant way, where you just write out a bunch of equations and do some equational reasoning. It's no fun. It's not really enlightening. So, I think I want to say, just take my word for it that this is associative. This thing forms a category. You can use methods from fibered categories to prove this in a slick way, but it's kind of more difficult. Now, if you remember, in any category, I was drawing diagrams like this, where our morphisms are boxes and our objects are wires. For this category in particular, I'm going to refine this language, and I'm going to say, instead of being a box with a left wire and a right wire, I'm going to say that a typical lambda from x plus x minus to y plus y minus, I'm going to draw like this as a box with 4 legs, where this is x plus, this is x minus, this is y plus, and this is y minus. If you do this, basically everything still works out. And the reason that everything works out is if you remember, when we have parallel wires, we can interpret this in a monoidal category, and it turns out, so later I'm going to put a monoidal structure on this category of lenses, and secretly, when I have an x plus labeled wire, this is really referring to x1, where 1 is the one element set, and x minus is really referring to, this is x plus is the name of this set. So this is x plus 1, and this is 1 x minus. And then when I put them in parallel, this is going to be the monoidal product of these two things, which is going to be just Cartesian product on the top, Cartesian product on the bottom. And so that gives you x plus x minus. So I'm secretly using the fact that every object can be decomposed into this kind of a positive thing and a negative thing. So the positive things I'm going to draw as arrows pointing forwards, and the negative things I'm going to draw as arrows pointing backwards. Okay, I will come back to this graphical language. I want to give some examples of things that you can do with this category. So the first example is probably going to be the most hand-wavy, because I'm going to pretend that we're physicists and we can just throw infinitesimals around. So suppose you have y is f of x and f is some differentiable function, then dx is dy over f prime of x. This is just taking dy by dx is f prime of x and rearranging. So secretly, I'm doing some stuff involving cotangent bundles, but I'm just going to do this intuitively and say, okay, we have some infinitesimals. Now, what I can do is I can bundle this data into a lens, which I'll call it L of f. I'm not going to write down its type because its type involves some cotangent spaces. But I want to say that this thing plus the forwards part is just f. So, and the backwards part, x dy, is going to be dy over f prime of x. So, so what I'm doing here is, if I put in some x, I get out y, which is f of x, and then if I put back in some dy, I get back dx, which is dy over f prime of x. And now, if I take two of these, if I take some other function g, and then I do and I compose them like this. So the thing along the top is just the composite fg. So if I put in some x, then here I'm going to get f of x, and here I'm going to get g of f of x. And then if I ask what's the thing along the bottom, this is going to turn out to be the correct derivative of fg given by the chain rule. So if I put in here some dz, then here I get, how should this be? This is going to be dz over g prime of f of x. And then, so this is dy, and then here I'm going to get dy over f prime of x. And if I substitute in this thing, this gives me the derivative of fg by the chain rule. So actually this particular form of the chain rule, this is what in computer science this is called reverse mode automatic differentiation, and it's also called backpropagation. So this is doing the chain rule in this particular form is the kind of basic trick of how machine learning works, I think. Okay, you can probably formalize this. So really what I'm doing here is I'm taking some very extremely standard thing from differential geometry, and then I'm just saying, okay, the space is flat, the space is just Rn, so my cotangent bundle is actually a trivial bundle, and this is what you get. So it's kind of differential geometry without the interesting parts. Okay. So that's a motivating example for this category. So it turns out that the composition in this category kind of correctly encodes the chain rule for derivatives like this. Another thing you can do think about something like a Markov decision process, only let's ignore probability for now because probability is a bit of a headache. So imagine like a deterministic version of a Markov decision process, which is not very interesting. So we have some state space which is called Q state. And it's a finite, okay, so it's a finite set. I'm in computer science mode here and say my state space is a finite set. Here we have an action space. And we're going to have a transition function. So transition says that in every state, for every action we can do, we transition to a new state. So we have a transition function, which I'll call small q, going from q times a to q. And then I have a payoff function, which I'll call u, going from q times a to the real numbers. So let's say I'm living in some state space, I'm in some current state, I can do an action, then after doing that action I'll transition to a new state and I'll get some payoff. And then I want to do this repeatedly. So in a typical setting, the most basic setting of dynamic programming, the transition function will be stochastic, and then I'm looking for the policy, which is a function from states to actions, saying what action I should do in each state, in order to maximize the sum of the payoffs that I get as I go around this transition system, except that this is an infinite thing, so then I have to have a discount factor, and I maximize, say, the discounted sum of these payoffs. So what I'm going to do is I'm going to ignore probability to keep life simple, and I'm going to talk about one single stage of this process. And then I'm also going to ignore the part where I said maximize, because this comes later with the game theoretic part. So if I fix some action, if I fix a policy, that's what I want. If I fix a policy, pi, which goes, so this is going to be a deterministic policy, so it goes from states to actions. Now I can package this into a lens, which I'll call L of pi, and this is going to be a lens going from Q reals to Q reals. Now, what this is going to be is along the top, so L of pi plus, this is a function from Q to Q. So given some initial state, what's the next state? It's going to be, oh, I shouldn't have called that Q. Call this, I don't know, X. This is the initial state. So this is just going to be the transition that we get from that state given our policy. And the backwards thing, so now we take an initial state and a real number, and the real number is going to be interpreted as a continuation payoff. And I'm going to define this to be the payoff that we get from doing the action that our policy says in the current state. So it's going to be big U of x and pi of x plus once discounted continuation payoff plus beta U. So we have a discount factor. So now if you think about composing several of these things end to end, what this is going to do is apply the policy several times. So we're going to go through several state transitions, and then it's going to kind of discount the continuation payoff in the appropriate way and then add the payoffs that we get from the transitions that we just did. So let's say I take L of pi, L of pi, L of pi. So say I take 3 copies of this. So here we have Q, 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 Now, if I put in some initial state Q and then ask what happens along the top, well, it's just we get the state that we get from following our policy for 3 steps. So we transition, we transition, we transition. And then the backwards thing takes the initial state together with the continuation payoff to, so this, we're going to get the payoff given by this, which is U, careful, I'm using small u and big U here, maybe that's not the best choice. Big U is the general payoff function, small u is the continuation payoff. So we get, this is the payoff today, plus discounted. Okay, so I could kind of do this a little bit more from first principles. So we get discounted continuation here, and the continuation here is given by the composite of these things. So this is now going to be u of, and now we're going to replace x with, let's call this, let's shorthand this, otherwise this will take forever. Say that x0 is the initial state, and then x1 is going to be the transition. In general, xi plus 1 is going to be the transition of xi given the policy. So we get this infinite sequence of states that we go through given x0 and pi. So this is going to be x1 pi x1 plus discounted, more brackets, and then we get the third thing. So this is going to be u x2 pi of x2 plus discounted, and now I've done as many as I wrote down, so now we actually put in u. So you can see that this thing is creating this discounted sums piece by piece. So if I take a limit as I add more and more stages to this, then the backwards function of this converges in an analytic sense to the actual infinite discounted sum of payoffs that I get from following the policy. Okay. Okay, another example. And then that will be the last example, and I'll go back to theory. Of course, when we start writing down concrete games, there will be lots of examples coming from examples of concrete games, concrete examples of games. Okay. Suppose I have a stochastic process, which is, so having told you that this construction doesn't work over the category of stochastic processes, I'm going to fake it by embedding it in the category of sets. So suppose we have a stochastic process which I'll call f. So f is a function from some set x to distributions on some set y, or equivalently, f goes from x times y to 0, 1 plus some conditions. I'm going to use the first form for this, I think. Think about Bayesian inversion of this. So suppose we have a stochastic process and we have a prior distribution on its input, and then we have an observation of its output. We can Bayesian update to get a posterior on its input. So given a prior, which I'm going to call, so prior begins with the same letter as policy, so I'm going to call this also pi. So given a prior, which is a distribution on x on the input, and given an observation y, which is just a point in y, we can get a posterior, which I'm going to call this is a new distribution on x. I could write this down, but well, maybe I should write it down. The definition of this thing is by Bayes' law that so this is a distribution on x. So the probability that this thing takes some value x is going to be, so actually what is this? It's the prior probability Hang on. I've got to get this right. Weighted by the sum over all of the x's that make, so we observed that after applying f we got the observation y, so x such that, this is going to be this sum over all f primes, this weighted by the transition probability that f went from x prime to our observation. I think that's right.
You need one of those on the top as well, don't you?
One of what?
Sorry, am I wrong? It should be p of x times p of y given x over p of y, right? So it does that. You need p of y given x and then put that down.
P of y given. Oh God. So this thing is p of x given y. So this should be, and this is p of this p of y. Yeah. So this thing should be p of x times p of y. So
p of x times p of y given x. Right. So you need the f of x times f of x of y on the top, don't you?
Yes, I think so. Not 100% sure about that. Should have checked this before coming in. Okay. I mean, the exact details of this aren't super important because, again, you can just take my word for it that this works. If you define the posterior correctly, then, okay, so observation is that we can, so this operation here, so this data defines a function from dx times y to dx. So this is the type. So this is given a prior, given an observation on the output, we can get a posterior. Before I was using superscript plus and superscript minus, and this is supposed to be a dagger, not a plus. That's probably a terrible choice in notation. Let's call this there we go. That's INV. I think things I write very small on the board can't be seen clearly in the video. This is INV for inverse. Okay. This isn't quite in the right form to define a lens because these sets don't quite match up. But it turns out I can do a linear extension. So if I have a function into distributions that's defined just on a set, I can extend it linearly. So I can pretend that f is actually defined on distributions of x just by linear extension. So if an element of this looks like a mixture of elements of y, so I can just apply f pointwise and then take the appropriate mixture in the image. And like I say, this is something that you do informally all the time, that you have a deterministic function, something that's not defined on random variables explicitly, but then you plug in a random variable anyway. The other thing is that this is a generic operation on monads, and I'm applying structure of the probability monad here. Okay, and given this, I can also linearly extend just along y. And I don't think it's obvious that this is a sane thing to do. But it turns out surprisingly to me that this is a reasonable thing to do. So I'm linearly extending this Bayesian inversion along, so instead of observing a point, I'm now observing a mixture. So my observation, say, comes with some uncertainty. So that's the interpretation. If my observation of the output is also itself coming with some uncertainty, this is the Bayesian updating that you do. That's probably where the confusion was with this extra term. That in my original setting, this was going to be 1, I think. Okay. By the way, I'm also hand waving over what happens if we make an observation which has probability 0 given our prior. In that case, this is undefined, but I'm going to ignore that. So now I can collect this into a lens from dx to dy. And it turns out that the operation of lens composition also does the right thing on this. So if I have some other stochastic process from y to z, and I do the same trick, and now, okay, so I have a composite stochastic process, which will say the transition probability from x to z is the sum of all the ways that I could go via y. This is the composition in the category of stochastic processes that I defined last week, that's secretly just matrix multiplication, basically. And it turns out that if you do this, then the backwards map that you get given by lens composition is the correct Bayesian, is the correct way to do Bayesian inversion for this composite process. So this is the chain rule for Bayesian updating. And this is so I'd say in summary, there is a nexus of things which people have looked at and said, that kind of looks like the chain rule. And basically all of them live in this category. So none of the observations is new. I think the categorical formulation of this is possibly new, I'm not sure. It's simple enough that somebody could have easily done something like this before, say in differential geometry or something. Okay. That's a bunch of examples to motivate this category. You can do a bunch of things in it. This is not touching on the fact that you can do game theory with it, although this decision process thing is basically strongly hinting towards how this works in game theory. Okay. What should I do next? I should say a bit more about the graphical language of these things. Okay, let's clean some boards. Actually, I should give one more example, which is the example where the name comes from. So these things are called lenses, which is a term that came from database theory. And the original purpose of these things in database theory was for destructive updates of data. So, and there's several slightly different variants of this, but the basic idea, the basic formulation is, say I have some function from x to y, and I'm going to think of this as a relatively trivial function like a projection. So I think of this like a product type, and this is a projection onto one of its factors. Okay, maybe I should give an extremely computer sciencey example, like say that this is the state of a database, and then you run a query on the database and you get, or say you have a table in a database, you run some query on it, you get a subtable. Now suppose you want to do a destructive update on the result of the query. So you want to take some cell in this table and erase its contents and replace it with a new value. But this operation has been done on the results of this function, the results of the query, say, and you want to propagate this update back to the original, the whole thing. So we have some function which I'll call get. So this is like retrieving some data, some subdata, I'll say. And then we have a function called put, which says given the initial state and given a new, so given an update to the results of running this function, we can propagate it back to the original thing. And it turns out that if you chain these things together, if you do a function and then you do a function of the function and then you want to do a destructive update on the final result, and then you want to propagate it back to the start, notice I'm secretly using language like chaining and propagating back. This thing also goes by the chain rule. So database theorists were studying basically this structure purely for this purpose. And it turns out, so they kind of, in my opinion, wrote this more clearly than, than most mathematicians have done. And so by focusing on this structure specifically, then it turns out that this thing is useful much more generally. So this is why I call it lenses, because they are the only, of all the different people that use things of this form, they are the only ones that gave a decent name to these operations. A thing with a forwards part and a backwards part like this. This is called a lens because you're like looking into part of a data structure. It's focusing on part of a data structure. That's where the name comes from. Okay. Of course, if the destructive update operators satisfy a bunch more conditions, there are algebraic axioms that need to hold for destructive update operators, and that gives you a lot more structure, which in general doesn't hold for any of these other examples. Okay, so a fairly big chunk of the computer science literature on this thing needs to be thrown away because it doesn't apply to all of this, or to game theory. Okay. Also, right now, there's a small community of people doing some extremely mind-blowing things with this idea called optics. So it's a huge generalization that's extremely nice. It's got extremely heavy category theory involved in it, and it's fun. Okay, more on the graphical language. So I hinted at we were going to put a monoidal structure on this category. So now I might as well say it. If we have x plus, x minus, and we have y plus, y minus, I'm going to define the tensor by just Cartesian product on the top and bottom. So x plus times y plus. There are two different conventions, but it's sometimes convenient to do it back, the other way around along the bottom. Of course, this is just isomorphic, but this is sometimes convenient. The extension of this to morphisms, to lenses, is basically immediate. So you don't have to do anything complicated like the sequential composition. So if you go from x1, y1, x1 plus, x1 minus to y1 plus and y1 minus, and you start getting lots and lots of names here, and then x1, x2 plus, x2 minus to y2 plus y2 minus. Then, if we want to take a tensor of these two things, these two morphisms, this needs to be a lens from x1 plus times x2 plus x1, x2 minus times x1 minus 2. And then the same thing over here with the y's. Then on the top, this just takes a pair x1, x2 to this function of x1 and this function of x2. And then along the bottom, we have an x1 and x2 and a y1 minus and a y2 minus. And we just do the only thing we can do. We take this x1 and this y1 and put them through the backwards thing of here to get an x1 minus, that's this. And then the same things with the 2's. So this is just applying functions in parallel. And it turns out that this forms a monoidal category. So after doing all of that, we can perfectly well draw pictures of arbitrary networks of these things like this, and like this, and like this, and like this, and nothing goes wrong. And at any point in one of these diagrams, okay, so let's do this example is silly, let's do a reasonable example. Let's do a picture of the thing I just did. So we have a lambda going from x1 plus, x1 minus, y1 plus, y1 minus, and a mu going from x2 plus, x2 minus, y2 plus, y2 minus. Now, this no longer looks sensible because previously all of my things had 4 legs. And this diagram has 8 legs. So if I take the boundary here and say what is the type, what is the object on this boundary, I'm going to say the top thing is the Cartesian product of all the forwards arrows. So this is x1 times x2. And the backwards thing is the Cartesian product of all the backwards arrows. Reading from bottom to top to be consistent with this notation. So that's x2 minus times x1 minus. So for a complicated network, I can take a cut through the middle, and I can just say what's the object on that boundary. You've got to pay attention occasionally because you can have 2 different graphical boundaries referring to the same object. If we have this thing, x plus, x minus, this thing refers to the object x plus, x minus. And if I do it the other way round, x minus, x plus, so I've permuted, I've just drawn these the other way round. This still refers to the object x plus, x minus. Because the product of the forwards things is still x plus, and the product of the backwards things is still x minus. What this means is that if I draw 2 crossing wires like this, this doesn't really mean anything. This is a fancy notation for doing nothing. So the object on the left and right boundaries is the same, and the only sensible interpretation of this is the identity on that object. Okay. For any, okay, there's a couple more things we can do. Maybe I should keep this board constant the whole time, because that actually has the definition clearly written down. Okay. If I have a function from x to y, I can lift this to a lens from x1 to y1. Because the thing along the top needs to be a function from x to y, that's what we have, and the thing along the bottom needs to go from x times 1 to 1, and there's only one function into the one element set. I'm going to draw this with a special notation like this. Now, think about what's the object referred to on this boundary. The top thing is the product of all the forwards things, which is x, and the backwards thing is the product of all the backwards things, and there are none, and the Cartesian product of no sets is the one element set. And then similarly, so this is consistent. And I can also lift it to I can lift it contravariantly as a lens from 1 y to 1 x, because the thing along the top is a function from 1 to 1, there's nothing, and the thing along the bottom is a function from 1 times x to y, which is a function from x to y. So I'm going to draw this like this. And again, if you think about what's the object referred to on this boundary, the forwards thing is the product of all the forwards things, which is the one element set, and the backwards thing is y. Okay. So we have these two operations. If you want me to use fancy languages, I have a functor from the category of sets to the category of lenses, and then I have another functor from the opposite category of sets to the category of lenses. I can also combine these. I can combine these into a functor from set times set up to lens. So if I have an f from x plus to y plus, and I have a g from y minus to x minus, then I can combine them together into a x plus x minus to y plus y minus. Maybe I should write this down. If I have a f going from x plus to y plus, and I have a g going from y minus to x minus, then I can combine them into a function that I'll call fg, going from x plus x minus to y plus y minus. And I'll give this and this thing is the tensor product, according to the thing which I hand waved over here, of the lifting of f forwards and the lifting of g backwards. So I'll give this the notation like this. So x plus, y minus, x minus. Okay. Another thing I have is that for any set x, there is a canonical lens going, which I'll call epsilon sub x, which goes from x to 1, 1. And 1, 1, by the way, is the monoidal unit, because if you take Cartesian product top and bottom with 1, you get the same thing. So this thing is pi, and it's denoted by empty space. So for any x, I have a canonical lens from xx into empty space, and I'm going to give this the special notation this. X. So this is x forwards, this is x backwards. So again, boundary here, the object, this is consistent because the object referred to at this boundary is product of the forwards things, which is x, product of the backwards things, which is x. This boundary, there's nothing, the object is 1, 1. Okay. Now it turns out that for any function f, Okay, let's. Is this board clean? Yes. If I, okay, fix a function f from x to y, then I can get from here to y by doing f and the identity on 1y. And you can stare at it and think what this should be. This along the top needs to go from x to y, that's f, and then we need to go from x times y to y, that's a projection. We can also go to x, and this is the identity on x times f backwards. I didn't give this a notation. I just invented one. So this is, forwards is from x to x, that's the identity. Backwards needs to go from x times x to y, and this is going to be f of the second one. Okay. Now I have two different ways of going into 1, 1, because I can do epsilon of x here, and I can do epsilon of y here. And this diagram commutes for any f. So what this means, right, to prove this again, you just have to write down a bunch of equations and stuff for 5 minutes. What this means is that if I draw the upper path as a diagram, I get, so f is this, the identity on backwards y is this, x, y, and then I'm sequentially composing with this epsilon operator, which I'm writing as a bent wire like this. So this is what the upper path looks like as a diagram, and the lower path, so this is y labeled, and the lower path is this. So it turns out that these two diagrams refer to the same thing. Okay, so you can play this kind of game that you can find equations that look nice graphically, and then you can try to prove them. Not all the things that you would like to be true are true. In particular, we have a way to bend wires this way. So you might ask, well, can we bend wires this way? And it turns out that you cannot. So for this, you would need a lens from 1, 1 to x, x. And the forwards thing has to choose an element of x. And there's no way to do this canonically. And if you try to cheat, it won't work, because some conditions that you need to hold will not hold. So this is not allowed. So our graphical language is a bit weird. So we have these directed arrows, and like these kind of isotopies do hold, but we can't bend wires this way. So we don't have complete freedom to draw anything that we like. This ends up having a game theoretic interpretation, because the kind of information flow that you get that are allowed in a lens, it's just like, so the forwards things and the backwards things are qualitatively different kinds of information flow. So the forwards thing is just functions. So this is like normal information flow, normal causality, that the input causes the output informally. But the backwards things, so the backwards things can often feel, I won't say teleological, this is a philosophical term. And I'm using this because of how it ends up looking in game theory, that the backwards things, so if you think back to the decision process example, the backwards things was a real number. And it's the real number that's being kind of given by the payoffs from the future. So this is something like this. So my backwards thing is going to be something like my payoff on my optimization target, and that's allowed to depend on the future. That's allowed to depend on ordinary actions that haven't happened yet, which is what you want in these kind of game theoretic systems and so forth. This is the reason that economics is harder than physics, because causality doesn't go the right way. So the dependence of this kind of teleological causality on ordinary causality only goes one way. You can't go the other way. So you can't take some payoff based on something that hasn't happened yet. So what this is saying is we can take an ordinary action and now I can consider it as an optimization target. I can't go the other way around. So I'm not allowed to take some real number that depends on some things that haven't happened yet and then play a move that's based on that. If you do that, bad things will happen. So I can't quite explain this clearly. I'm trying to get at, this is like, this structure kind of is encoding something crucial about the type of causality and information flow that are allowed in game theoretic systems and related things in some way that I can't quite put my finger on. Of course, what this has to do with examples like backpropagation of derivatives, I don't know. That might be a coincidence, possibly. Yeah. Okay. Okay, I've now decided I'm going to spend the entirety of this week on the structure of this category, and open games are going to come next week, which means that what was going to be in lecture 3, which was going to be some things possibly including repeated games, will probably never appear. Because just building up the appropriate amount of structure just takes way too long. Yeah, I'm a theorist at heart, and I'm really focusing on the theoretical foundations of this. I wish I could say more about the ways in which you can use it for practical modeling, but I understand the theory better, so I'm going to say more about it. Applied compositional game theory. That would be fun. Okay. Having introduced this graphical language, I'm going to introduce a completely different graphical language for the same thing, which is going to be more convenient in certain settings. So a lens from x plus x minus to y plus y minus, which I have been drawing like lambda from x plus x minus to y plus y minus. By the way, I should say you can open the box. Given the structure which I defined on this board, everything like this can be decomposed. If we open the box and look inside, every lens looks like this, that we copy this thing and apply. So lambda plus is now just a function, so we can lift it going forwards. And lambda minus is similarly just a function. This is y minus, and then this thing gets bent like this. So it turns out that every morphism like this decomposes like this. Right. I can draw this in a completely different way, in a completely unrelated graphical language, like this. So now This is going to be x plus y minus x minus. This restores the property that all the information is flowing from left to right. So all of the inputs come in on the left. So this is an input, this is an input, and then all of the outputs come out on the right. This is an output, and this is an output. So when you say it like this, a lens is like a function that kind of has two stages. You give it an input, it gives you an output, and then you give it another input, and it remembers what happened before, and then it gives you another output. So I can also, like I opened the box here, I can open the box here. So this tells you how information flows around this thing. So I give it some input x, it gives me an output lambda plus of x, and it remembers a copy of x. So this bar across the top is like its memory of what happened in the first part. And then I give it another input, and then given that and what it remembers, then it gives another output. And composition of these things, now instead of being the first thing on the left and the second thing on the right, this now goes by, I call this bigger fish composition. So you put one around the other. Like this. Okay, so if I have, I should start using two colors just to make it easier to see where each one begins and each one ends. Unfortunately, the red doesn't come out very well on the video, so I'm not sure let's try orange. The red was almost invisible on the video. So this is the first thing, and then the second thing looks like this. And then I just wire them together like that. And now imagine just kind of putting these in a box which has this shape. And now you can just read off the definition of the composite. So you can see how this output depends on this input, and how this output depends on the two inputs. So this is an alternative graphical language, which in many ways is very convenient. So in fact, you can you can draw pictures of the chain rule. You can draw pictures of Bayesian updating of stochastic processes in this way, and it's kind of nice. Okay. Now, the other thing that's nice about this is I can extend the number of legs, and the definition is kind of obvious that all the outputs can just depend on all the inputs that are strictly to the left of it. And this turns out to be crucial. So open games end up involving three-legged ones of these as well as two-legged ones. Okay. Now, having said I was going to spend the whole time on this, I overestimated how long I'd want to talk about that thing. So let's give the definition of open games again. Okay. So, open games are going to be the morphisms of a category. And the objects of this category are going to be pairs of sets like before. So the diagrams of open games are going to look basically the same as the diagrams for lenses, the first kind. And sometimes I'll use the second kind as well. So, an open game G from an object x plus x minus to an object y plus y minus consists of 3 pieces of data, and before it was 4, so I've reduced it by 1. Consists of, okay. So the first thing is the same thing that I said it was before, which is a set, which is the set of strategy profiles. So set sigma of strategy profiles. Okay. The second thing is for every strategy profile, a lens of this type, which I'll call G of sigma. Okay, so the first thing that an open game is an indexed family of lenses, and the indexing set is the set of strategy profiles. So each strategy profile is naming a lens from the input to the output of the same type as the open game. So if you think back to the decision process example, I, in that, fixed a policy. And now you can see what I would have done with that if I had already said what an open game was properly, is I would take sigma to be the set of policies, and then I would take G of sigma to be the lens that I got from fixing that policy. Okay. Now, the third part is the interesting part. So the third part is going to be a relation, by which I mean a subset, which I'll call E, which is a subset of sigma times 2 more things. Lenses from 1, 1 to x plus x minus. That's the input type of this. Times lenses y plus y minus 2, 1, 1. That's the lens from the output. So and an element, so a pair consisting of a lens like this and a lens like this is going to be called a context. So if I have an open game that looks like this, x plus x minus y plus y minus, then a context is just going to be a way of kind of closing it.
Sorry, question. You didn't say what x and y are. Are they just sets?
These are just some arbitrary sets. So, yeah. Oh, yeah. There's 4 arbitrary sets. So this relation says, given a context, which of the elements of sigma are equilibria in that context. Now, this set from lenses 1, 1 to x plus x minus, what are they? Well, we need a function from 1 to x plus, which is just a choice of element of x plus, and then a function from 1 times x minus to 1, and that goes away. So the set of lenses of this type is actually canonically in bijection with x plus. So, okay. And the lens is y plus, y minus, 2, 1, 1. So, in many classical categories, if you take the category of groups or the category of topological spaces, if you take things like this, these are called points, and they actually behave like points or elements often. So a thing like this in the category of groups is just an element of that group, and topological spaces is just a point in that space. So this is kind of typical. These things are called copoints, and in most of the categories that you come across day to day, these things are trivial. There are no non-trivial copoints. This is different. So a lens like this consists of a function from y plus to 1, that goes away, and a function from y plus times 1 to y minus. That's a function from y plus to y minus. So this thing is canonically in bijection with functions from y plus to y minus. And if I was giving a talk to category theorists at this point, I'd be saying the words representable functor. Okay. So if you can remember the definition of open games that I wrote down last week just to scare you, we can now see that this definition is equivalent to the one from before, because so if we have a lens like this for every sigma, then this is really a function from sigma times x plus to y plus, and a function from sigma times x plus times y minus to x minus, which is the thing which I called coplay. And then this is a subset of sigma times x plus times the function set from y plus to y minus, which I think I wrote it down in the form of functions from these to the power set of this, which is the same thing. So this is equivalent to the definition that I wrote last week by applying all of these canonical bijections. However, if I told you that the things that I wrote last week were the morphisms of category and said, try to come up with the composition law and show that it's actually associative and unital, and has the properties that you need, this is extremely painful. Whereas this basically becomes a category almost for free, and all of the hard work goes into what we already did, which is fiddling with the category of lenses. So let's talk about sequential composition of open games. Okay. So suppose I have an open game from x plus x minus to y plus y minus, and another one which I will call g, and then another one which I'll call h from y plus y minus to z plus z minus. And I want to know what's the composition. So in pictures, this is going to be g h x plus, x minus, y plus, y minus, z plus, z minus. So I want to know, how do I interpret a diagram like this? Okay, now the first thing I pretty much have to just tell you. So the set sigma is intended to be the set of all the possible behaviors without any restrictions. So a behavior of a composite, a possible behavior of this composite is just going to consist of a behavior of this thing together with the behavior of this thing. So the sigmas are going to compose by Cartesian product. So this I just have to tell you. Sigma sub, and I'll start writing subscripts for this data for referring to different open games. So sigma of GH is going to be sigma of G times sigma of H. Okay. Now, the second thing, so GH, this composite, needs to have a family of lenses from x plus x minus to z plus z minus indexed by elements of this, which is this. So the lens which is referred to by some element of this, so sigma is going to be some element of sigma g, and tau is going to be some element of sigma h. And now this needs to be some lens from there to there, and you can probably guess what this is going to be. This is going to be the lens composite of g of sigma and h of tau. So this thing is composition of lenses. Yeah. Now for the interesting part. When should some sigma, so we have this GH, and we want to know when is some sigma tau a Nash equilibrium in some context. And it's a context of GH, so it looks like this. I'm going to call this H. I always call my context H and K, where this is called the history. So H is for history and K is for continuation. I don't know why continuations are called K in computer science, but they are. So when is some behavior of this composite a Nash equilibrium in this context? Well, so to be a Nash equilibrium, you want to be a Nash equilibrium on each component, but in a different context. So G is now living in a context in which the history is still H, but the continuation is now this thing, except, well, this isn't a lens, this is an open game, but we've been given a strategy profile for it, which means that we can specialize this, because H has an index family of lenses indexed by tau, and we have an element of tau. So what this means is that we can now consider G in the context H and H of tau followed by K, and I can kind of put this in a big box. And this is why it was useful to define this in this back-to-front way and say, well, this is under the hood just a function from, in this case, from z plus to z minus. But if I view it as a lens from z plus z minus to 1, 1, then I know how to interpret this composite, because this is just another lens composition. And similarly, I can do the same thing for H, so I can adjust the context for H by specializing G given sigma and putting this in a box. Okay, let me write this down and then try to say it in a better way. So, the equilibria of G, so this needs to be a subset of this times this times this. So it's going to be the set of things like this, such that two conditions. One is that sigma H and then H tau K is in the equilibrium set of G, and then tau H G of sigma and K is in the equilibrium set of H. I've screwed up writing this down. This thing is EGH is the set of triples. Yeah, that's better. EGH is the set of triples satisfying these two conditions. Okay. So there is some extremely Nash equilibrium style reasoning happening here. So secretly I'm here talking about unilateral deviations. So think of this equilibrium set negatively. So imagine that strategies are Nash equilibria by default, and then they fail to be Nash equilibria precisely when some concrete player has incentive to deviate. So think of Nash equilibrium as a kind of negative property in that sense. So now think of these things as being made up of a bunch of decisions, and I'm taking when I compose together, I'm taking something like a disjoint union of these decisions. So in order to have a Nash equilibrium, in order to fail to have a Nash equilibrium here, either someone has to want to deviate here, or someone has to want to deviate here. And these deviations are unilateral. So what that means is so I want to say, does somebody want to deviate here unilaterally from sigma, given that everybody here is playing according to tau? I don't have to, because I'm considering unilateral deviations, this is why this trick works. Because I'm considering unilateral deviations, a unilateral deviation in G means that I can assume that everybody in H is playing according to tau, and vice versa. So then I want to check, does anybody in H want to unilaterally deviate from tau? And in that setting, then I can assume that everybody in G is playing according to sigma. And when we get concrete examples, these lenses are going to end up kind of encoding how these contexts adjust themselves. For example, K can end up encoding a payoff function. So imagine something like a sequential game where, so this is going to be player 1, Say this goes away, this will be player 1. This is going to be player 2 in parallel with some stuff that pipes around the extra information, because the payoff function also needs to know this value. And then it also, so this thing is feeding back the payoffs of both players, and then it needs to pass back just the payoff for player 1. We'll come to real examples like this next week. This is getting ahead a little bit. And then this composite is going to end up being the payoff function from player 1's point of view, given that player 2 is playing tau. So we specialize to the move which player 2 is doing given tau, and then we also do the backwards part, which ends up, in this case, just eating the payoff for player 2 and passing back the payoff for player 1. This is a good time to stop. I will end with, because we've proved that, because I've claimed without proof that lenses form a category, that this composition is associative. This thing is just built from lens composition and the logical AND operator. Like, this is true and this is true. And Cartesian product. And remember from lecture 1, I'm outrageously pretending that Cartesian product is associative. It's only really associative up to natural isomorphism. So basically for free, we get that this thing is a category, that this composition law is associative. All of the difficult work to prove this is associative has already been done, whereas if you do it the other way around, which I actually did in the first place, that I proved that this was a category with the raw original definition from last week, this is a fairly painful exercise, whereas this is kind of slick. Okay, and that's the end.